Hello everyone, welcome back to another class of fundamentals of particle and fluid solid processing. In the last class we started with the concept of fluidization. Today we will go into the details of estimating minimum fluidization velocity. We have already understood that what is minimum fluidization velocity, what is bed expansion, and how it varies with or when there is the gas velocity or the fluid velocity, how the pressure inside the bed varies from a fixed bed to the fluidized bed during this expansion or this transition, how this parameter varies, that we will see today. So, to start with, if we have sufficient fluid superficial velocity, okay, when it goes to the minimum fluidization velocity, that is the UMF we designate here, MF stands for the minimum fluidization velocity, then the onset of bed expansion occurs, which means the bed starts to expand and it goes till a point when there is the maximum voidage that is possible for that kind of packing. So, with further increase in the velocity, we have the bed as fluidized. So, now if you consider about the scenario that we have seen for the fixed bed case, that we had velocity, superficial velocity, we have a packed bed of particles, and then we increase the velocity, we saw that till a point there is this variation, this is the linear variation, okay, in case of laminar flow. That is the first part of the Ergun equation. Then if we start continuing increasing the superficial velocity, what will happen, that we have repeatedly have heard and discussed, that the bed will now start to expand, the voidage will start to increase, okay, and until the point it reaches its apparent weight, that is just balanced by this upward thrust, that till that point the bed expands and the pressure does not change with that much, okay, it remains some kind of a constant value. So, here this parameter is the pressure gradient that is mentioned here against u. So, it reaches a maximum pressure value, okay, then actually if we look into details, then we will see that it drops because of this increase in porosity or voidage in the bed. It slightly drops, okay, and then again it increases, okay, because this drag force now becomes dominant after a certain period of this superficial flow rate, okay. So, this pressure gradient increases due to the frictional drag of the fluid on the walls when that is transporting these solid particles, okay. So, we have a moment, okay, where the whole bed is fluidized, and then we have the transport region where now the particles are being carried with the fluid or the fluidizing fluid. In between that some period of time, the pressure gradient basically decreases, the pressure drop per unit length that decreases, and that decrease happen, as I said, due to this increase in the voidage. The particles or the bed, it have now a smaller weight of the particle per unit height of the bed. This is the balance between that we have discussed, balance between the apparent weight, okay, and the pressure gradient. So, this is what basically happens during the fluidization. What happens with the pressure drop instead of pressure gradient, which is the pressure drop per unit length, if we look into that, we see such profile that we have already discussed during a problem. So what happens that if you now simply plot del P versus U, you get a linear profile, you get a point, okay, till this end of this point A, line A, you have the minimum fluidization velocity, that is the onset of fluidization. After that, for a certain period, the bed expands, okay, and as the voidage increases, okay, pressure drop slightly decreases, and then it remains unaltered for a period until the transport happens. Okay. So then if you come back on the same line, like we went from this point to the end of point A by increasing velocity, further increment in velocity leads to point B, further increase in velocity we have a point C, after that the bed expansion is completed, okay, and the pressure drop remains unaltered till the point, let us say, D. Now from this stage, okay, if you now decrease the superficial velocity or the fluidizing fluid velocity, it would follow this path D to C, okay, then to E instead of going through this B path, and it follows this EF path. So when we have the highest voidage possible, from there if we decrease the superficial velocity, it would follow a same linear path but not identical path while increasing the velocity. There are several studies which relates or finds expression between the startup and this shutdown procedure. If I say in a startup operation and its closing down or the deaeration process. So this is the characteristics of fluidization or the fluidized bed. So we have the pressure drop and velocity, and in the previous slide I showed you the pressure gradient versus the velocity. The reason, I hope, is now clear to you, that from a fixed bed, as we increase the superficial velocity of the fluidizing fluid, what happens? The bed starts to disengage, the expansion happens, reorientation of the particle happens, it finds its maximum porosity with those particles by reorienting themselves, so that the flow resistance inside them becomes lesser and lesser and the minimum value, okay, and then the transport region occurs after a certain period, until and unless it cannot withstand that much pressure gradient, the whole apparent weight of the bed cannot withstand further the pressure gradient of the bed. The transport happens, and as the transport happens, we know that as the suspension flows or such kind of flow happens, with increasing velocity, again the pressure gradient increases due to the drag exerted on the wall. Fine. So this UMF or the minimum fluidization velocity can be determined experimentally by increasing and decreasing velocities, these two lines, and plotting this pressure drop versus velocity results as we have seen. Okay, and practically when we get the intersection of these two straight lines or the best fit between these experimental points, while increasing and while decreasing the superficial velocity, we get these two pressure drop lines, and when we plot those or find the best fit, linear fit, and we have the intersection between the two lines, that is detected as the minimum fluidizing velocity. So, typically linear plots are popular than the logarithmic plots, but logarithmic plots are important or becomes unavoidable when there is a non-linear pressure gradient against velocity in the fixed bed. And when that happens, you know that when that flow regime shifts from laminar to the transition or the turbulent region, then the pressure drop does not vary linearly with the superficial velocity. Then to have this straight line intersection, you must plot those on the logarithmic plots. So, this is the effect or the influence of fluid velocity on the packed bed to the fluidization, or during fluidization the influence of fluid velocity. So, how do we estimate in other way this minimum fluidization velocity? Typically in fluidization, when we say the pressure drop, it is basically the weight of particles minus the upthrust on the particle, okay, by the bed cross sectional area. Okay. This is the balance we have already done. If you remember, this balance we have already done, that this is the pressure drop of the bed or the pressure gradient that happens in the bed balanced by the apparent weight of the bed, and this is the apparent weight. Solid fractions, relative density multiplied by the G. Fine. Now, if you remember again or recall the Argan equation, okay, we can write this expression, because if you think of it's kind of a similar manner that the flow is happening upward in a packed bed until the minimum fluidization velocity. This relation should give you an estimate, if not the accurate answer, for the pressure gradient, because until that minimum fluidization velocity the bed is not fluidized. So, you can think of that is we are having a fixed bed structure, but with the maximum porosity. So, the point is that if we use Argan equation until the point of this minimum fluidization velocity, we can replace then this del P expression in fluidized bed at that fluidizing state here in place of this del P. Okay. So, we have this relation. We further simplify this relation, okay, because there are so many terms or so many parameters involved. So, it is wiser to convert it to some dimensionless number which will essentially involve these parameters, but in a unified way. Okay. So, this is further rearranged by this manner, that we deliberately multiply or try to find out the very common flow dimensionless number is the Reynolds number. So, we try to write those expression in this form in each of the term, the first part and the second part. So, for that whatever the parameters we have multiplied here, we divide that. Okay. So, to have this mu at the denominator, we have multiplied that with mu at the numerator as well. So, basically we again rearrange this expression to find out or to express this relation in a non-dimensional form. or non-dimensional number. Okay. So, if you do this, okay, and this is nothing but the particle Reynolds number at the minimum fluidization velocity or minimum fluidizing velocity. This is the Reynolds number square. Okay. So, this parameter is here 1 by this parameter. So, the right side is basically simplified in this way, that this is 150, again at this stage this 1 minus this thing goes out, 1 minus epsilon. So, you basically have 150 1 minus epsilon by epsilon cube Reynolds number at the fluidizing velocity or the minimum fluidization velocity, 1.75 multiplied by 1 minus epsilon cube Reynolds number square at the minimum fluidization velocity. And this parameter we have already seen earlier, it is another dimensionless number called the Archimedes number. Okay. Or if we clearly write that, this has this expression. So, which means between the Archimedes number and the Reynolds number we have a relation, okay, that involves the minimum fluidization velocity. The Reynolds number expression is having the minimum fluidization velocity into it, and the Archimedes number deals with the fluid properties. So, this from this relation we have, on one hand, this is the relation between the Archimedes number and Reynolds number at minimum fluidization velocity. This now here at this case, at this minimum fluidization velocity, typically the maximum voidage in such case by, for the case of spherical particle, okay, this maximum porosity that in the minimum fluidization velocity has been seen to be of 0.4. So, if we replace this value in this expression, okay, so then we can find all these expressions are simplified and we get Archimedes number and Reynolds number at this minimum fluidization velocity with these coefficients for spherical particle. And when an Wu has had proposed similar correlations that fits a wide range of particle, okay, or wide range of sizes, it covers spheres and this much of Reynolds number or the particle Reynolds number for sizes larger than 100 micron. So, which means once we have found out the relation between this Archimedes number and the Reynolds number at the minimum fluidization velocity, based on this all other parameters here, because here usually all these parameters will be known to you, because you are handling the fluid, you have chosen that fluid, the particles are also known, the size, mean size, okay, and here these parameters are also known except the UMF, and this minimum U that would be required to have this balance between the Archimedes number and the Reynolds number will give you the minimum fluidization velocity. And there are several such relations in the literature, okay, which helps for a range of particles or for a range of different size particles to have or to calculate the minimum fluidization velocity. And this relation, as it's shown here, has some restriction to use, or in other way it can be used safely if these criteria are met. So, I hope the estimation of minimum fluidization velocity is clear to you. The other relevant property that we look or that we consider during this fluidization, okay, for particles less than 100 micron, like in the previous slide we have seen the particles of more than 100 micron, we had relations for that. Then other researchers have also come up with a UMF expression for particles less than 100 micron. So, which means we have expressions, because this fluidization based has been our area of interest or research for a long time, for several decades. Okay. So, there are sufficient amount of information of this minimum fluidization velocity for any kind or any shape, any size of particles. Whenever that is required, we should choose the appropriate one for our design purpose. Now, as I said, the other parameters that are relevant or are typically we must know or we should be dealing with during the fluidization are the particle density. Now, in fluidization, particle density is basically not the absolute density. There are difference between the particle density and the absolute density of the particle. The absolute density basically deals with the density of the solid material by which that particle is made of. But in fluidization, particle density is the mass of particles divided by its hydrodynamic volume of the particle. Now, what is hydrodynamic volume? Hydrodynamic volume is the volume that is seen by the fluid or inside the fluid, okay, including its pore or with pore, voidage, everything. So, if this is a solid particles having pores, okay, and this is the only solid material, so this dotted surface, the whole dotted surface is basically the hydrodynamic volume, including its pores. But the absolute density is basically the mass of a particle divided by the volume of solid material making up this particle or that has been used to make this particle. We have other term which is called the bed density. The bed density is defined as the mass of particles in the bed. The mass of particles, like in particle density we had mass of a particle, here we have mass of particles in the bed divided by the volume occupied by the particles and voids in between them, which means we have a relation between the particle density and the bed density, which is that rho b, the bed density, is equals to solid fractions multiplied by the particle density. This bed density for these particles or the particulate solids also similarly refers to as the bulk density for powder, for powdery materials or very fine material. So, we will be frequently dealing or calling these names from now onward, that in fluidization what is the particle density, what is the bed density, which is the equivalent for the powders as bulk density. So these are the relevant parameters, okay, that we should remember, and these are easy to remember. And what are the relation between the particle density and the bend density? If you remember these expressions, you can always derive that, or if you remember these expressions, you can remember what are the expressions for that. Now, as I said, it is similar to the powders, or the bulk density for powders, okay, or for the fine material, because the point is that you should understand, or you should remember, that the powders will be very compact when it is packed. It would not be of similar behavior when there are granular material, or let us say the materials of considerably bigger size. For example, the behavior of flowers or wheats is different than the behavior of gravels, or even the building sands. Okay. So in the next class we will be seeing this characteristics of the powder in fluidization, or how the powdery material, how the powdery state actually influence the fluidization characteristics, or how this characteristics when there are powder inside a bed, and how the fluidization is influenced. So these things we will be elaborating in the next class in details. Till then, thank you for your attention.